Let's go with question 1. So question 1, it says define the moment of a force. So the moment of a force is defined as the product of the force and the perpendicular distance between the line of action of the force and the turning point. So you want to make sure you include that the distance is the perpendicular distance, okay? And the perpendicular distance between the line of action of the force, meaning where the force acts, and the turning point. If you want, you can top this off with the equation for moment, which is moment is equal to F times D. It won't hurt to add that. Okay, the next question says, state the principle of moments. Okay, so the principle of moments states that if a body is in equilibrium, the sum of the anti-clockwise moments about a point is equal to the sum of the clockwise moments about the same point. The things that you want to ensure that you mention in your answer here are, if a body is in equilibrium, you must state this. You might want to write it as, for equilibrium, you can even write it like that, the sum of the anti-clockwise moments about a point. So don't forget to include this. About a point is equal to the sum of the clockwise moments about the same point. Okay, so you need to include the condition. So it's for equilibrium, or if a body is in equilibrium, then you rattle off the sum of the anti-clockwise moments, but you must include about a point is equal to the sum of the clockwise moments about the same point. Okay, so now we move on. Part C says, a cyclist hangs his bicycle with the rear wheel in contact with the ground and the handle attached to a light string as shown in the figure below. The entire assembly is in equilibrium. The first question says to indicate by drawing arrows on the figure the forces acting on the bicycle. Okay, so the easiest force we can think of right now is the weight of the bicycle, okay? And so we know that the weight of an object acts at a single point called the center of gravity. So we can put that in very easily. We can draw in an arrow like this representing the weight. So that's the weight. The next one is the tension in the string. So this is a piece of string, they said, and we mentioned that the tension in the string always pulls, it never pushes. So it pulls on the bicycle like this. So this is the tension here. So this is the tension. Call this T. And then finally, there is the reaction. Remember, the reaction occurs where you have two surfaces interacting with each other. So at this point, where the wheel of the bicycle touches the ground, you have a reaction force. So we're going to put an arrow acting upwards and we're going to label that force R. Okay, so question 2 says, state two equations equating these forces. And so now this is where you have to use your knowledge of equilibrium to come up with these forces. So the key that they gave you in this question is that they said the entire assembly is in equilibrium. So you pull out all the information you know about equilibrium. What are the things that hold true when something is in equilibrium? First, there's the principle of equilibrium that says that the sum of the forces in one direction equals the sum of the forces in the opposite direction. So we can use that to write the first equation. So we look for the forces acting in one direction. So the R acts upwards as well as the T. And then the weight acts downwards. So we can write our first equation. We can write that the weight is equal to the reaction plus the tension. Okay, so that's equation 1. What's the next equation that we can come up with? we can use the principle of moments. The principle of moments where the sum of the anticlockwise moments about a point is equal to the sum of the clockwise moments about the same point. So let's make that point R. So let's say taking moments about R. After we decide that we're going to take moments about R, we have to look at the other forces acting on the bicycle and determine if it would create clockwise moments about this point here, or if it would create anti-clockwise moments about that point. So let's look at the weight. The weight would create clockwise moment about R. And the distance that the weight is from R, because remember the moment is the product of the force times the distance, the perpendicular distance between the line of action of the force and the turning point. So this distance that we're interested in is this 0.8 meters here. Okay, looking at the tension now, the tension would cause the bicycle to move anti-clockwise about R, and the distance, the perpendicular distance that the tension acts from the turning point is this distance here, 1.75 meters. So in finding the moment of T about R, it would be T times this distance. So let's write that. Okay, so taking moments about R, it means that, okay, so we can write that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Okay, so the clockwise moments is created by the weight, so we can write that W times 0.8 is equal to T times 0, not 0, T times 1.75. And those are our two equations. Okay, so the next question says, the bicycle has a mass of 20 kilograms. Use the results you obtained in part C2 to determine the tension in the string. So, okay, so I brought over what we just determined to be the two equations and I wrote them there. And so we need to basically use this information to determine what is this tension here in the string. Looking at this equation, look at this first one. We have three unknowns and we can find out what the weight is because they gave us the mass and they gave us the gravitational field strength. So we can find out what the weight is, but we don't yet know what the reaction is. So we can't use this equation just yet. But looking at the second equation, we have two unknowns, or we can say we have only one unknown because we know what the weight is. So let's go ahead and try to solve for T using this equation. So let's find the weight. So the weight, remember the equation for weight is mass times the gravitational field strength. So if the mass is 20 kilograms times gravitational field strength, which is 10 newtons per kilogram, then the weight is 200 newtons. Okay, so that's the weight of the bicycle. So we just want to take the weight and substitute it into the equation we chose. So substitute W into the chosen equation. So what we will get is 0.8 times 200 equal to 1.75 times T. So we see that we only have one unknown, and so we can solve for what T is. So 0.8 times 200 is 160. So 160 is equal to 1.75 times t. And if I continue on this side, we want to solve for t. So let me just go ahead and do it the long way. That's 160 is equal to 1.75 times t. So we want to divide this side by 1.75 and we want to divide this side by 1.75. Okay, so these two will cancel and we end up with t is equal to 160 divided by 1.75. So that will give you 91.4 something newtons. What we want to write, if we were to write our answer to a correct number of significant figures, we would have to choose that answer as 90. So it'll be 90 newtons. The reason why is because we look back at the values that we multiplied and we saw that the smallest number of significant figures that we multiplied was 1. So 0.8 only has one significant figure. So our answer would be most accurate if we wrote it to one significant figure. So that's approximately equal to 90 newtons, correct, to one significant figure. Okay, I have a challenge for you. The challenge takes us back to the two equations. The principle holds if we take clockwise moments and anti-clockwise moments about the same point. So I want you to write what this equation would look like if you took moments about t. Okay? And then in the second part of this question, you're going to use your two equations to solve for what t is. Okay, so that's your little challenge. You can try it on your own.